Every atom has some sort of standard structure, but now, imagine a mad scientist. Picture the classic image of one, and think about this. Suppose this scientist decided to assemble an atom from particles that aren't actually suitable for the job. For example, using only electrons to make an atom, or replacing some of the subatomic particles inside the atomic nucleus. You might think that nothing would come of it, right? But that's not the case. Something will come out of it. What you'll get is new matter, or rather, a new substance that will have some interesting properties. And you'll also get so-called exotic atoms. Yes, exotic atoms are those in which the standard set of subatomic particles has been replaced. That's what we're going to talk about today. And every time we note that there are certain interactions within an atom. There is the strong interaction, the weak interaction, and the electrostatic interaction. The atom's structure is the way it is, or rather, it's better to say the atom's construction turned out the way it did, because in this configuration, the particles that make up the atom achieve the best balance of all these interactions. These particles ended up together not by accident. It was precisely this combination of properties that made it possible to assemble atomic nuclei from them, and in fact the atoms themselves, and then to form matter from atoms. Now imagine that you take those particles that, in theory, shouldn't be able to coexist. Well, the first question is, why are you doing this? And there was this interesting thing related to the proton's radius. The essence of the paradox is quite simple. When we replaced the electron in the atom with a muon, it turned out that the proton's radius did not match what we expected to see. Based on the computational models, the combination we're considering should work for both the muon and the electron. And for the electron, all our calculations work out and everything is correct. But when we recalculate for the muon, we encounter a certain problem. It turns out that the model we're using might actually be incorrect. And it might be incorrect because essentially, in it, we are substituting one value for another. And if everything is correct, then, roughly speaking, the variables should cancel out. Of course, I'm exaggerating a bit. But to put it simply, both for the muon and for the electron, we should be getting the same values. But we don't see that. This is just one example of why we need to use exotic atoms. And exotic atoms also include, for example, anti-atoms, like that very same antihydrogen. Antihydrogen is a magnificent, incredibly fascinating thing, which means that with its help, we could finally get a tangible grasp of antimatter. And to some extent, we have managed to do just that. For example, it was once assumed that you could make anti-gravity engines out of antimatter. And that really would have been the case if antihydrogen hadn't fallen in gravity. But alas, it fell too. And yes, antihydrogen is essentially also an exotic atom. And here I'll also mention that in just a few minutes we'll come back to antihydrogen as one of the examples of exotic atoms. There are quite a lot of exotic atoms. An exotic atom is always something non-standard. Exotic atom. Most often it's a certain particle that is made up of components not typically used for this purpose. But since we first mentioned muonium, let's start with muonium. Muonium is an interesting atomic model where the electron is replaced by a muon. A muon is a strange subatomic particle that has the same charge as an electron, but is about 200 times heavier. If a particle is 200 times heavier than an electron, it makes sense to assume that the forces of interaction between this substituted electron and the atomic nucleus will also be 200 times stronger. And that's exactly what happens. In practice, when we look at the behavior of muonium, which is the name for an atom where the electron is replaced by a muon, it turns out that its orbit becomes significantly compressed. Again, it's mechanics, and strictly speaking, that's not entirely correct. You are, of course, right. But for us to grasp the essence of the discussion, it's enough to use mechanical analogies. In reality, everything there is determined by kinetic energy. By the way, we've talked about this in one of our previous videos as well. But for now, let's just ignore that and proceed as if that's the case. Due to the large mass, the orbit of the muon, when it takes the place of the electron, becomes compressed. As a result, we get a very interesting structure where an electron muon orbits around the nucleus. And at the same time, the radius of such an atom decreases significantly. And it decreases because in fact, the outer orbit of those electrons, where they would normally be, also contracts. A muon exists for only hundredths of a second, but even that is enough to observe how it behaves. First of all, to check our logic regarding the proton and to find out whether the calculations for the electron are correct. For some reason, the calculations for the muon don't match up, which is very strange. This means the mathematical pattern might actually be incorrect. This allows us to observe the interesting structure and behavior of this atom, and it generally shows that we can confidently replace one particle. Replace one particle in the atom with another. Replace the electron with a muon. And interestingly, here's what happens. It happens in a fairly stable and standard way. We pass a stream of muons near the atom, and the atom captures muons in place of some electrons. Basically, it's like, I don't know, like a dandelion, but in reverse. If you take something electrified, or better yet, imagine some kind of sticky surface onto which you've blown a dandelion. These dandelion seeds stick to the sticky surface. Something similar happens when a stream of muons flies past the nucleus of an atom. The muons are captured from the stream, and that's how we get those very muonic atoms, the atoms we can work with. That's how it works in the laboratory. In practice, this doesn't happen in everyday life. However, there is a hypothesis that somewhere in a far, far away galaxy, somewhere out in space, under certain conditions, such processes might occur. Now imagine that an atom might not have a nucleus. Would such a structure still be considered an atom? Well, in the general sense, no. But in laboratories, such a setup is distinguished. And this kind of Frankenstein can exist for a while. It's even more unstable than polonium, but for certain purposes it's interesting. For what purposes is it interesting? It's interesting for testing various quantum physics hypotheses. And thanks to such a structure, we can once again test our logic regarding other particles. What are we talking about? We're talking about positronium. What is positronium? Well, you can probably guess that it's an electron and a positron somehow bound together. And what exactly is a positron? A positron is the antiparticle of the electron. It's an anti-electron. And so you were probably right in thinking that in positronium, an electron and essentially an anti-electron or positron are joined together in one structure. Under certain conditions, it turns out that an electron and a positron form a kind of bond. A complex bond built on a group of different interactions. And this kind of structure turns out to be quite stable, at least for fractions of a second, for milliseconds. This stable structure behaves like, I don't know, imagine something like nunchaku or something similar. This object spins in space, and as long as it doesn't fall apart, it represents a stable, well, supposedly stable structure. By the way, speaking of anti-atoms. I promised to talk about antihydrogen somewhere at the very beginning. So what is antihydrogen? Well, let's recall the structure of a hydrogen atom. It's one of the simplest atoms that exist at all. What do we have there? Basically a proton and an electron. Those very diagrams you always see in illustrations. That's a proton and an electron. This is probably the simplest system that can form and claim the title of an atom. So, scientists thought that if you replace the proton in hydrogen with an antiproton and the electron with a positron, you would basically get antihydrogen. Why not give it a try? And that's exactly what they did. It turned out that the system can be assembled. However, this isn't exactly news. People have been talking about it for a very long time. The logic itself has been tested for a long time, but there has been and always will be one main but. Antimatter, and what we ended up with is nothing other than antimatter, is extremely difficult to preserve. Why? Because it annihilates instantly. And why does it annihilate? Well, here we need to recall the classic diagrams that show what happens with such particles. In most cases, when particles meet, antiparticles and particles, they, roughly speaking, turn into pure energy. And this very transformation applies directly to the antihydrogen that we obtain. As a result, antihydrogen, the very one that was produced, is one of the most expensive substances in our world. It is the most valuable type of matter, whose cost far exceeds, well, many times over, the price of gold. And why is that? Because it's practically impossible to store it. By the way, antihydrogen is absolutely stable. It doesn't fall apart like ordinary hydrogen, but this holds true only until it, so to speak, sets foot on the path of our real world. So how did you obtain antihydrogen? Quite simply. There are accelerators that work with antiprotons, and there are various magnetic traps, electromagnetic traps. The antiprotons were slowly placed into an area where there are positrons, and between them, the very same forces formed that operate for ordinary hydrogen as well. Interestingly, these forces do not depend on the sign of the charge. More precisely, how? Of course, they do depend on the sign of the charge, but essentially, the magnitude that interests us does not change. There also exist so-called hyperons and strange atoms. Scientists, as always, were getting creative, you could say, searching for the truth and thinking that the truth was somewhere nearby. And indeed, the truth was somewhere nearby, because in their view, if you replace one subatomic particle with another, you might get something incredibly interesting. Overall, this line of thinking is very useful and correct. And so, in an attempt to do this, one quark was replaced with another quark. There is such a thing as strange quarks. Strange quarks are different in that they have a greater mass than ordinary quarks. If we replace one quark inside the nucleus of an atom with another quark, the particle will decay differently. And if you replace one of the protons or neutrons with a lambda hyperon, the system will behave completely differently. Lambda hyperons are, roughly speaking, subatomic particles that contain a strange quark. The strange quark is heavier than ordinary quarks and has a special quantum number, or strangeness, which is conserved in strong interactions. That is why particles containing a strange quark behave unusually and decay more slowly than their counterparts. Nevertheless, when a lambda hyperon is inserted into a nucleus, a hypernucleus is formed, and the atom is called a hyperonic atom. And these hyperonic atoms are interesting to us because they most likely exist in neutron stars. Why? Because in order to create such a thing, you need to use the ranges of forces that are found inside neutron stars. The next interesting point is replacing one of the protons, for example, with an antiproton. This thing will simply be called an atom with an antiproton. This is a real gift for nuclear physicists. Why? Because when we look at how a system behaves, when we place an antiparticle directly into the nucleus of that system, we can literally observe the atom falling apart in real time. The antiproton will sink deeper and deeper, and as a result, the atom will disintegrate. But while it's sinking in, we actually observe some interesting processes. A Rydberg atom, on the contrary, is a very large atom or an atom with a highly excited electron. Its radius increases significantly because the electron moves far away from the nucleus. And how is this achieved? Well, basically, a significant amount of energy is transferred to the electron, moving it to an outer level. If we can figure out how exotic atoms appear, how they form, and why they form at all, then we can answer a whole range of these questions. That's why knowledge about exotic atoms is extremely important.